So what I'm going to say is all in the paper defended toward the unification of physics and number theory. So I won't say anything that's outside the scope of what we demonstrated there. And whoever remembers that paper will probably be able to follow this shorthand because I'm going to be quick. But it's interesting, okay? So, all right, so for any simplex, such as the 100 simplex, there is a quantity of n minus m simplices within it, which is exactly the quantity that are called prime simplexes. So simplex integer is just a number. It's a more powerful number than a digital number because the essence of a number, as said by one mathematician, is the set theoretic combinatorics within the number. Now, of course, an arbitrary symbol, such as how we draw 5, does not have any self-referential symbolism in it, and it certainly doesn't in any way, as a symbol, describe the set theoretic combinatorics of the number, the integer 5. However, when you look at simplex integers as symbols representing integers, it not only gives you the numerical count of the integer itself, just as your arbitrary integer does in digital integers, but it also gives you the full set theoretic combinatorics in a very non-arbitrary way in a principle called self-referential symbolism. So they're powerful, these simplex integers. And I want to describe a very important difference between digital integers, which are arbitrary man-made symbols as integers, versus non-arbitrary simplex integers. It can be understood with a simple idea. So when we're talking about the Riemann hypothesis and the distribution of primes, we're really trying to, it all ties in to the ability to predict the quantity of prime numbers that exist with some arbitrarily chosen bound along the number line. And so the method of, when we use digital integers, in order to get them to converge, we have to invert them, okay? So when we do this and we continue the series to convergence, we see at the end this beautiful relationship to a number that you normally associate with geometry, which is pi. So we get this beautiful convergence written with pi. With simplex integers, we don't need to invert them. Okay, so I'm going to write pi here because I want you to pay attention to the fact that it's a transcendental irrational, right? Which means it doesn't have an algebraic expression. And when we use simplex integers and we study something such as the circumradii, the series, first of all, the circumradii series going from the 1 simplex to the infinite simplex ranges the span of 1/2 to square root of 1 over square root 2. So that's the span. So the circumradii of every single simplex integer fits within this bound. So if we only pay attention to the prime simplices, and it converges rapidly, okay? The distribution of primes thins out as you go deeper down the number line. It becomes more sparse. And so we'll call that the numerical density. So the numerical density becomes more sparse with digital integers. The spatial density on the one-dimensional line also becomes more sparse over space. So spatially and numerically, you have sparseness as you go further down the number line. It's very interesting with simplex integers because the numerical density, of course, trivially, is identical to the, in other words, when you look at the density, when you look at the quantity of 23 prime simplexes within the 100 simplex, it's a trivial thing. There's 23, you know exactly how they're spaced out. So what you do is you take the circumradii of the first one of the first prime, which is 1, and that's 1/2, so you can draw that as a circle. And then you take the circumradius of the next prime simplex, and so on, and what you get is a set of concentric rings. And you can draw a line through the set of concentric rings to get a one-dimensional distribution. And numerically, that distribution drops in density identically to the distribution of prime density numerically. But unlike the digital integers, which also drop in spatial density, the distribution in prime density of the simplex circumradii on the one-dimensional line actually increases in density. It's very, very interesting because you go further and further down, and because of the extreme rapidity of convergence of this value to this value, which is a distance value, it far surpasses the increase or the rapidity of the thinning out of the digital. So you can get a ratio that you can study here for prime number theory. So you have this ratio, which is with simplex integers, which is your spatial ratio, your spatial drop in density. So you pick a span and you say, I want to calculate what is the drop in density of prime simplex radii over space in 1D. And you get a number, okay? And then you'll get another number when you analyze what the density numerically is and how that drops. So this density increases, and this density, numerical density, decreases. And for some span of primes, there's a calculable ratio that can be used. So you can go to different equal spans along the number line, and you can check, is the ratio of these two, this increase in density and decrease in density, is it the same no matter where I go? Does it change depending on what span I take? And what's the rate of that change? How can I analyze how it changes from span to span in terms of the ratios of these numbers? The point that I'm making is that there's more rich and non-arbitrary information in simplex integer number theory than there is in digital number theory. So the next thing that I'll add to this is two problems. The first is that problem that I just defined. You know, it's been some years, but I don't want to be too distracted from prime number theory. But I want to tell you about quasi-crystals and how it relates, and this is the second problem. It's a harder problem. That problem that I said is a one-day problem for someone like, you know, Ray or Todd or somebody who's played with this. And it's a problem that's never been written down in the literature, I'm sure of that, from the research we did when I made that paper. The other thing is quasi-crystals. So Freeman Dyson says, he argues and explains from a mathematician's point of view why the distribution of primes and the distribution of non-trivial zeros is a quasi-crystal. So the thing about quasi-crystals is one can say that a proper quasi-crystal is some unknown irrational projection of some unknown periodic lattice in some unknown dimension. Okay? So the problem is that set is so large, it's an infinite set. How do we know, how would we possibly know how to start searching through that set of projection, you know, hyperlattices and projections that would generate the same aperiodic point set that you get on the distribution for the non-trivial zeros or the prime numbers themselves. But what you can do is you can understand that each prime simplex maps to an A lattice, right? So an A series lattice. So for example, the simplex integer for the number 4 is the 3 simplex, because it's the equidistant array of 4 points in 3 space that describes, through its lower dimensional simplices, the exact set theoretic combinatorics for the number 4, or the number 1,000,000, or any number. And so then you can say, you can extend that, and you can say, well, can I study prime number theory through these geometric numbers by the A-n lattice series? And of course you can, such that within the A100 lattice, you have within it 23 prime A prime A lattices. And the distribution of those prime A lattices within the A100 lattice is exactly the distribution of primes on the number line. And so where you want to try to do analysis is by irrational projection. So you can project that A100 lattice down to 1D by an irrational value. And you will get a point set, which is quasicrystalline in 1 dimensions. Now the trick is, how do you isolate out in that projection the prime A lattices so that you can study the distribution of prime A lattices within this point set? It's a very tricky and confusing problem to think about. But I stopped thinking about it because I felt it was distracting our physics work.
Can I repeat the problem?
So I described one method of doing prime number theory by studying the ratio of the drop in density numerically over the circumradii of the simplex series, and as a ratio of the spatial density, which increases. So it's the prime number, the prime simplex. So let's say this is a prime radius, and this is not a prime radius, and this is not a prime radius, and so on. And you have a distribution where you say, I'm only studying in this series of circumradii of these simplexes the distance between the radii, because they're numbers that are lengths. So then you have this aperiodic distribution of points that represents the circumradii of the prime simplices. That's one way. And that's the one problem that I suggest is about a day's work of somebody who understands this, and it's not a hard problem to work, program a solution for in Mathematica and kind of understand. But a really hard problem is a more sophisticated way using quasicrystal mathematics, and that would be to understand a simplex by extension into the A lattice. So the simplest n-dimensional building block of any A series lattice, A2, A3, and so on, is the n simplex corresponding to the A series lattice. And so similar to the statement that the distribution of 23 prime simplexes within the 100 simplex is exactly the distribution numerically of the digital integer primes within the span of 100. I want to come back to this for a second, because the way that we study the Riemann hypothesis for 100 years in prime number theory is to use the prime number theorem, and it's a way to predict in every case, an incorrect prediction of the quantity of prime numbers within a bound. It's never right in any case, but the larger your span of numbers that you're counting primes in, the more accurate the prime counting or prime number theorem counting method is. So that if you go all the way to infinity, okay, it would be accurate, but any finite bound is always inaccurate. And it's the inaccurate. So for example, when you're doing 100, the prime number theorem, which is based on the other most popular transcendental number with no algebraic expression, E, that gives you a significantly wrong number. So they're 23, it gives you 19, very wrong, right? And it's the wrongness, through a really complex mathematical process, it's the wrongness of the prime number theorem prediction that maps to the non-trivial zeta 0 distribution. That alone is a very sophisticated proof that I don't even understand, but that Ray assures me is true and that we put in the paper. And it's in our paper. But I couldn't reproduce the math to show that mapping. But let's assume it's true. So then, therefore, the deepness of proving the Riemann hypothesis is understanding why this prime counting function based on a transcendental number is always wrong in every case, and how that wrongness maps back to the distribution of the non-trivial zeros. The non-trivial zero distribution is very much the same problem in a more sophisticated form as the problem of understanding what in the world causes and allows one to predict the distribution of prime numbers in any bound along the number line. So as you can see, when you analyze this question, why would there be 23 prime simplexes within the 100 simplex? Okay, you can clearly see the answer to that question, the way I've posed it, is a purely geometric question, where geometry makes contact with set theory, group theory, number theory. But it's a deeply geometric problem nonetheless.
So I remember you play with these binomial coefficients, remember?
Yes.
With those simplexes, and I remember that it was a relationship between the binomial numbers, remember, right?
Yes,
I remember. Okay, I remember vaguely, yes.
So I don't want to go over my time, but too much more. But Marcelo asked a question. I'm still in the process of answering it. And then Mia wants to ask a question. I'll let you go before me if you don't mind just going.
Okay, it's a very quick question. Not regarding to Riemann hypothesis, but in what you say. Would you consider, so what's the what do you think is so interesting about this prime and simplex? Would you say that it would be maybe words or letters in the code? How would you correlate this
to how we think about codes? Well, what we're doing is we're trying...
Infinite, right? Like,
yeah, I mean, how it might correlate, I'm not 100% sure, but there's a lot of papers, in addition to the one that Carlo and Ray and myself did on showing how there's this mysterious and very interesting correlation between quantum mechanics and prime number distribution and the Riemann hypothesis. It's very deep. Nobody has the convincing killer answer, because perhaps the convincing killer answer requires some deeper understanding of why it's been 150 years and we still are seemingly on the wrong track with proving the Riemann hypothesis. So back, is that okay? And so how it relates to the way I think everything is symbolism. And I don't like arbitrary symbols because anybody could make it up. I like self-referential symbols that are non-arbitrary, like mathematical objects such as n simplices. And those things encode non-arbitrary intrinsic meaning in mathematics. And so, of course, our whole program here at Quantum Gravity Research is about trying to use self-referential symbolism, of which form is quasi-crystals, which are languages or codes made of self-referential symbols with syntactical freedom and so on. So somehow this eventually, when we figure out our program, we're somehow maybe going to have deeper insights into all of mathematics and number theory, and where does number theory converge with the physics, right? And
I think that definitely could, they look like a very good candidate to being the symbols of the words.
Yeah.
The only thing that I'm trying to understand, I don't know if I have I probably don't have the answer yet, is how this alphabet, this concept of symbols would be infinite. Like, why you would need this? I feel like it should be like limited in something.
I don't think you do need the infinite simplex series, but we know that mathematics is what nature is made out of. Most of us believe, like many other physicists, that nature is not approximated by our mathematics, that somehow we're starting to get glimpses of how nature is literally made of mathematics, and geometry is mathematics. So we live in a geometric reality. So it's this deep idea where you think about all of mathematics is an upside-down pyramid, starting with your choice of set theory or number theory, right? But in my opinion, counting numbers come first, because you can't count sets without counting numbers. It's hard to study set theory without numbers. But we could say set theory is more fundamental. Okay, but just so you guys know, I have one more thing to say, which is answering Marcelo's question, and then I'm done. But we can put you first, Ray.
Yes, it will be short. I will just to explain to everyone here what is our geometric criteria of primality. It's that if you have a simplex of any dimension and you are counting the subsimplex of any dimension, for example, for a tetrahedron, you are counting the points, the edges, the faces, and you are coloring them, for example, for a tetrahedron in 4 colors, you should have the same number of point and element of each dimension of each color. And for the tetrahedron, it doesn't work, so this is proving that this is not a prime number. For the pentacoron, it works. Everything can be colored with 5 colors. So if you can see in high dimension and virtually make this coloring operation, you can, in one glimpse of view, see that this number is prime or not.
Okay. So on all of this,
just
guys,
one comment on this.
Okay.
In the connection with quantum mechanics and quantum computation. So if you have a problem with more degrees of freedom, more qubits, you have a higher dimensional Hilbert space. But you always can decompose this, and so that we can translate this to like a higher dimensional simplex. You can decompose in the building blocks, which is our lower dimensional simplex. Yeah, simplex.
Okay, so I'll say the last two things, which I want to answer Marcelo's question, which was my problem number 2 anyway. And then I want to point out why I was emphasizing these two transcendental numbers. So prime number theory is deeply involving these two numbers. This is what the zeta series converges to with another couple symbols here. And then the basis of prime number theory, whether you use one of the more modern derivatives of the prime counting function or the original one, it's based deeply on another transcendental E. And so whatever's going on, when you use this E, you get a mistake, an incorrect prediction, and then you map that prediction deeply to this Riemann hypothesis. So when you're dealing with simplex-integer number theory, to do the same types of problems, but you convert into geometry, you use algebraic irrationals. And that's interesting. It may not be important, but it seems to be an interesting difference to at least keep note of in your mind. So now the last thing is just defining the second problem. So the second problem is to study the spectrum of prime distribution within a projection. So this was a kind of thing that's artificial. Well, this is a manipulation of if I were to take 100 simplex, I'd have to go around it and find all the n minus m simplices that are embedded within it, and then take their circumradii and then plot all their circumradii out where they share the centroid of these circles, and then draw my line through it so I can derive my one-dimensional spectrum of prime simplex distributions. So one question is, when I do that and I do a Fourier transform, do I get discrete Bragg peaks indicating a quasicrystal mathematically, or do I not get discrete Bragg peaks? And so now, repeating what I said before, let's move beyond n simplices and take the extension of the n simplex series and study the problem the same way. So when we think of the simplex integer 3, it is the 2 simplex. And when we extend this out to its lattice form, we build out the A2 lattice. And so we can go to the 100 simplex again, which has 23 prime simplices within it, and we can extend that out to the A100 lattice, right? And embedded within the A100 lattice, there are 23 prime A lattices embedded within it. We take some irrational angle to project the A100 lattice to 1D. And the thing about irrational projections is they allow you to preserve a great deal of information about the higher dimensional object, whereas rational projections will cause you to lose a tremendous amount of information. So somehow, the conjecture that needs to be explored is, how would one mathematically analyze this one-dimensional spectrum from some projection of the A100 lattice to pay attention to the density distribution over space and number and their ratio of the A prime lattices that are represented within that one-dimensional irrational projection. But you don't have to do it in one dimension. You could do it to any lower dimension, like 2D. But it's a hard problem. So Ray and I thought about it for a while, and then we had already, spent a long time on the paper and the research behind it and all of that. And and decided to put the problem on hold. There is one more thing that I'll say relating simplices to prime numbers. So the prime numbers, when you study them via simplices, come in two mirror sets, which are equal. So if you go to infinity, half the primes are on one set in this base 6 structure and half are on the other. But we can understand the base 6 by first principles by taking we take the simplex series that gives the set theoretic combinatorics for each simplex, and that is Pascal's triangle. So when you look at Pascal's triangle, then what you're reading in that is the set theoretic combinatorics of any n simplex that relates to the line on that part of Pascal's triangle. It's the binomial coefficients, and then so when you then study that, and this is explained in the paper, when you study that, then you realize, oh, okay, there's really a fundamental non-arbitrary bifurcation of the prime numbers when you study it via simplex series, the set theoretic combinatorics of simplex number theory, which is expressed in Pascal's triangle, and then you get these two lines. Now the lines are decreasing, they're increasing in wavelength. Okay, if you just were to draw them out on the digital number line, and then you understand that half the primes are on one of these wavelengths that increases in these waves that increases in wavelengths, and they're offset. But so then, again, what is most interesting to me is the extra information or ratios that you get, because in the case of what I suspect that maybe man-made integers in some weird abstract way are not natural or a bit artificial. In a way they are, in a way they are not. Again, we're not talking about the symbols, like how we draw a 5. I'm talking about how you lose information. Because here, when I use simplex integers, I actually have a different delta, a piece of information between this sequential pair of integers and the next sequential pair of integers. It's a different distance. But when you look at the distance between 1 and 2, and then the distance between 2 and 3, it's the same distance. So it's that homogenization, that loss of information with digital integers that may be the root of this 150-year-old problem, which is really a 2,000-year-old problem if you go back to the mystery of how to predict or understand the pattern of prime distribution. So I believe this is an easy problem, is a one-day type of simple problem, and this other thing I'm talking about is a very hard problem because it requires, I have this all, I could write this down and tell somebody exactly what to calculate. With this, I can't, because I can't tell you what the irrational angle should be. I can't tell you if it matters what irrational angle it is, and I can't even tell you how in the 1D spectrum how you would eliminate the non-primes so that you could study the spectrum. I don't know, but I believe there may be answers to it. But this way is for sure straightforward. This method here gives you real distance numbers in this, and then the ratio. So that's it. So it's a very juicy problem. It's not our physics yet because we don't know what our physics is yet. But I have an intuition that there's a convergence in the future between number theory, prime number theory, and the Riemann hypothesis in particular, and fundamental physics. So if we were so bold as to speculate that our pathway is on a vector towards discovering nature's first principles, symbolic geometric code, then it's all very mathematical, and at the root of all mathematics is counting numbers, you know. So maybe but if I could find some person like Carlos or anybody that became interested, I'm going to give you the hard copy. Julia's giving you a hard copy now. If you study this paper, it's not like my essays. It's not talking about consciousness or a lot of essay type of stuff. There's some essay stuff in there because I can't resist, but what's in there that's rigorous, explaining this in greater detail, is very, very interesting. And you're so smart with both geometry and number theory.
Because remember, the connection between pi and the zeta function only occurs when s is even. When s is even, the zeta function it gives you a number related to pi because of the Bernoulli numbers. So it's the Bernoulli numbers that hold an important key in that.
So I actually think that somehow, in a weird way, pi and e, these two transcendentals, are problematic. I'm joking, but I don't trust a number that doesn't have an algebraic expression. I'm joking, but I'm saying that between two irrationals, if one has an algebraic expression and the other doesn't, I trust that algebraic expression. You know, it's less controversial.
If I tell you, if I give you the simplex, the n1000 simplex, can you tell me immediately how many primes they have?
No, I can
Without
tell
counting.
immediately if it's prime or not.
We have an algorithm that'll tell you without any effort that it's prime.
Because of the binomial properties of the binomial coefficients?
Yeah. It's by seeing, yes,
the binomial
seeing all
coefficients.
the sub-component of the different dimension, given where their number is given by the binomial coefficient.
Okay.
So if you can see them in n dimension in one time, you can see the symmetry.
I have a question. What is algorithmically more economical? The method of telling Carlos that the prime 1000 simplex has n primes in it, or him giving you the digital number of 1000? In other words, if you had to do it by digital numeric means versus this geometric means, which algorithm to tell you if it's prime is more economical?
So with the digital number, I use the Eratosthenes Kribel, the simplest algorithm. So I must test all the number before the square root of 1000.
So you got to do it by brute force?
By brute force with 33 number, and then I solve it.
And with the geometric, the simplex?
If I can see in n dimension, I can see it immediately.
Okay.
Well, but there's computational ways, mathematical ways to see. He doesn't mean visual. He means math. If he can mathematically, so it's harder.
Yes, I can see this for the triangle that 3 is prime, and I can see for the tetrahedron that 4 is not prime. But after that,
so not necessarily more, not more economical.
I see. But can you find a general formula, an analytical formula that predicts the number of prime simplices?
We didn't work a lot.
Do you have a universal formula that will tell you immediately if you plug in a number n equals 1000 and it will spit out the formula, or you can only do it by looking at the binomial coefficients?
Yes, we have to look. I know that there is a universal formula which will give you only primes.
Yes.
But there is not a universal formula. You put a number and it will say it's prime or not.
So
there is just algorithm.
I say Terence Tao, at least in the United States, is the leading number theorist at UCLA. And all those guys are using more and more powerful supercomputers and insisting on digital integers. It's like they don't have another option, because they don't know, they haven't thought deeply to critically think about analysis by prime number theory, where you have more things to analyze, as I tried to demonstrate. You just have more non-arbitrary things to analyze and find ratios on. I'm not saying it solves it, for sure. I'm saying if we've spent hundreds of millions of dollars around the world in 150 years in modern times, and we're using digital number theory and now with supercomputers to kind of deal with statistics, how about not statistics? How about go back to the question of why is there 23? This is a geometric object. It's a thing. It's a prime 100 simplex living in 99 dimensions. Well, why is that? Why does it have 23 prime simplexes? Why is the distribution the way it is? So it's not just the count of 23, it's the distribution, the spacing. Like, why is that there? Then you can simplify that in the way that I showed you with the rings, looking at the radii, and you can study it. And I believe these two series, I mean, primes really thin out. So it should surprise you that the circumradii actually increases in density, because if you really understand how rapidly prime numbers thin, right? You should say, hey, I don't believe you, Klee. Why should I believe that they actually densify over the length domain? And the answer is, you'll find the kind of demonstration in the paper, but the answer is because although the prime density thins very rapidly, it doesn't compare to the density increase of the circumradii.
Because the zeta zeros become very, very dense. The spacing, as you go larger and larger, the density of zeros becomes very large, actually.
Inversely proportional to the distribution of primes on the digital number line. But they're just inverse. But, here, here the interesting thing is that they are different. That this, let me just explain what I mean here. When I go, Fong, what is the circumradius of the 2 simplex?
Square root of 3 over 3.
Like, just give me a rounded number.
Oh.
It is. So this is 0.414.
Yes.
Okay.
So 1 over square root is 3.
So and this is 0.5. Okay. So it. No, this is wrong. So 1 over square root. 1 over square root.
It should be larger. It should be larger.
Oh, I'm sorry. This is 7. This is 707. This is
0.6.
Okay. This is 707. So what? So
0.06.
Okay. So 0.0. So look. So 0.06. So you mean
0.6.
0.6. So we got 0.6 from number 3 to number 4. We go to 0.6, which has already used up half, approximately, of your entire span that you have to stretch out. So when you start drawing these concentric rings, it goes like, and it densifies very, very, very rapidly, because the whole span is just 2.2. I mean, it's just the whole span is 0.2, right? Just the delta between this and this. So that convergence is much more rapid in density than the thinning of the prime distribution. So what I would study is I would start asking questions about these ratios. The first question I would ask is, well, if I take a really far, a far out span of 1 billion primes, right, but really far out, and I look at the ratio of these, and then I take another span further out that's the same size of span, and I look at that ratio, are they the same? Or if I take a longer span that contains the same number of primes, right? Are those ratios the same? So there's several derivatives of the same type of question that you could ask. And by answering those, which are straightforward math things to solve, you start gathering some data points that then narrow your deduction or your next set of questions or guesses, right? And I think that should be studied. The quasicrystal one's really hard, but it will produce, in principle, I can make the statement that in the projection of some A lattice to 1D, somehow embedded in that information is this prime A lattice distribution. But I don't know how to parse the information to study it.
What do you think will be the irrational slope, as you call the irrational projection angle, that will get you from the A simplex to the quasi-crystal in 1 dimension? What is the value of that tangent? Is it rather the golden mean or not?
Oh, I try with many different ones, and it's always the same that we see, which is noisy. So I've not found a specific angle which is better than
whose slope, whose tangent is a rational number.
The projection itself. We should use something different.
We should clarify noisy. We have no evidence that it's noisy. When we look at the point distribution, we can say it looks noisy, but until we do a Fourier transform, which we didn't, and we don't know if it's noisy or looks noisy. And that's the thing about quasicrystals with many inflations and deflations. Once you get past 2 and 3 and 4, 5 letters, you actually have a hard time visually distinguishing it between noise or chaos and non-chaos. You have to do a Fourier transform.
So you're only asking about the angle.
The angle when you project down to lower dimensions.
That's pretty much always related to the Fibonacci chain, which is arctangent and 1 over golden ratio.
Okay. But like, let's say you had the A4 lattice. You're saying you could just start with that irrational angle. So you take arc cosine 1/4.
I'm not specifically talking about the A, but in order to have the Fibonacci chain, right? That's what we have. The Fibonacci chain corresponding to a periodic chain on the upper lattice. So that specific angle
should relate it to
That's a
that
good
projection.
idea. So maybe for any AN lattice, you can find that angle and get a complicated Fibonacci-related a golden ratio-related quasicrystal. So if we took A100, for example, then we would find that dihedral angle of the A99s, the A100 simplex, and then try projecting that and see if that gets us to some interesting ratios between the two smallest lengths or something that has a golden ratio value. But Fang's right, even if it's not a golden ratio thing, it is a non-arbitrary angle. In other words, you don't want to just invent arbitrarily your irrational angle. At least taking the dihedral angle of that AN lattice is a good non-arbitrary choice.
I mean, so far the quasicrystal we get, we can kind of always find the Fibonacci in them, the one that we're interested in. Like A4, for example, if we generate the Penrose helium, that's another case.
Yeah.
Right?
Yeah. But Carlos, so my request to you would be look at the paper, derive questions that you have that, I think it's all clear, but find questions. And who knows, you might get really intrigued with the question. And if so, maybe we could do a collaboration together. We could pay you
What about your work on random matrices? Have you done any work on random matrices?
I would say a little, but not really a big
because
focus.
now you want to play, because now you're interested in tensor networks, right?
Yes. Now we are focusing on tensor networks.
Yes.
And my latest question is, so our irreducible quasicrystals that construct our dynamic higher dimensional quasicrystals in 3 and 4 dimensions are easily represented with matrix operations. However, when we look towards something like the Penrose tiling as a sort of interactive network of one-dimensional matrix operations, the 1D quasicrystal subspaces, then we wouldn't have to go to a hypercubic analog of a matrix. So we call it a hypermatrix or hypercubic matrix. Wouldn't do that. You would perhaps you'd try to take a formalism and say, all right, each of these one-dimensional matrix operations, right, that are obviously based on like the Z2 lattice, those all network together in an H3 or H2 symmetric case of the Penrose tiling. And so how do we invent a tensor network formalism where eigenvalues of different matrix operations and all the individual matrix degrees of freedom for the one-dimensional phase-on flips and actions.
What about when I talked to you guys about the string nets, when Avrik was here, remember? You had these ribbons in the Penrose tiling, and those ribbons look like string nets.
Yeah.
Remember, you guys did?
Yeah, but I want to restrict it and ask. Carlos, I want to ask. Look, can you take something like Elser-Sloan's quasicrystal and derive from it a tensor network formalism where each one-dimensional path is described by matrix operations and eigenvalues, but that you network it not in a hypermatrix, but in an H4 symmetric tensor network?
I see. Okay, I have to think about it.
Okay, thank you everybody for giving me the time.